The patterns in nature. So this topic is a continuation on mathematics in nature, and the objectives of the video is to introduce you to more patterns in relation to Fibonacci sequence. How do we derive the sequence itself, the relationships we can get out of the given sequence, how it's related to the golden ratio, the golden rectangle, and of course later on identify or compute for the nth term of a Fibonacci sequence using Bennett's formula. So our brain is designed to understand structure. It's simply designed to understand pattern. So even if that certain structure or pattern has a missing part or missing component, our brain will still be able to understand that. Now, suppose this example right here, what you're seeing is a picture that has missing parts. However, your brain would still know that this picture is a picture of a burger. Or our brain can still be able to read certain words even if that certain word has a missing letter or missing letters. Example for this one, a brand that you've already known, it's Adidas, and also this one. So that's Toyota. Why do we know this? Again, because we are exposed to these types of words, our brain can recognize it. It has been a pattern that is seen by our brain. Hence, again, we can so read it. There are even sentences that even if the letters were jumbled or not arranged properly or misspelled, what we know what it meant. We know what the meaning of the word is despite the misspelling. That's also the reason why, even if you shorten the terms or the spellings when texting, you are still able to read it as a complete word. In nature, we can see these things. The upper part is the river delta in Mexico. Then we also have the artificial capillaries put inside a chimpanzee, and we have the nephrons in the kidneys in the branches of the trees. At a glance, they might look chaotic, but in a way, they are chaotic but following certain structure. So in a bigger picture, they actually look the same, chaotic in the same manner. Other patterns could also be seen in our plants or anything in nature. The curved parts in the shell, even the Milky Way galaxy, the arrangements of the seeds in sunflower, and other things that you can actually see in nature are also exhibiting certain patterns that's not just applicable to one plant, it could also be applicable to other plants. Aside from that, we have certain um, life cycles. The life cycle of a man. So it starts with the fertilization of the egg cell and the sperm cell, and it becomes a fetus, and later on becomes a baby. It will grow until it becomes old and eventually die. There has no accounts yet of anybody starting as an old person and then going back to infancy. That's a different story. Perhaps there is a fictional story, the Benjamin Button story, but that's a fictional. Then we also have the pattern where we see the life cycle of certain animals, in metamorphosis ng mga insects, and even plants in their own right. So it has a cycle and it continues to follow unless there will be interventions from human beings. But nevertheless, the natural process is still in a certain pattern. Our daily routines are also considered patterns. These are things that you might just subconsciously do without further push, because again that's a part of what you usually do every day, like going to bed when you're sleepy or waking up, eating your breakfast or whatever things that you're used to doing. Now, for several years, no, several years. What I mean is, a person can be identified according to its his or her routines. The routines will tell you what this type of person is. Because again, it becomes an identity and your brain would recognize that. And kaya nga, if there are moments where police officers investigate the crime, you will be required, if you are somebody who witnessed the incident, you will be required to or if this person is something of interest, the people that person knew will be asked what the daily routine of that certain person, because it would tell the police what clues. It gives them clues. So again, there's importance in um, identifying patterns, even if it's not just in school, a requirement in school. Again, we function by following a certain structure. So with these structures, um, in math, we call most of these patterns patterns. And a very famous pattern is what we call the Fibonacci sequence. So, how do we connect Fibonacci sequence in nature? Before, in our earlier topic, you were told that the Fibonacci sequence exists in many natural things. So, what is where did this Fibonacci sequence come from? So it was originated or it was made popular by Leonardo da Pisa in his book Liber Abaci. So he introduced there a rabbit problem where suppose you have a pair of rabbit and that rabbit will give birth, and then the said pair of rabbit will also give birth to another set of pairs, provided that the resources are endless. So, how many rabbits will be produced at a time, and so on? It started there, but then it's. I think the better explanation for the rabbit problem is in the Mathegon virtual book, where it explains what happens next when the first pair of rabbit births a pair of rabbit, and this new pair of rabbit will have another pair of rabbits, and so on. How many rabbits will be there? So I've been talking about rabbits and so on, but that's basically where the Fibonacci sequence originated. Now, how do we generate the Fibonacci sequence? So although it's a given, but if we are to continue it, in what manner do we continue it? So in most cases, the Fibonacci sequence can be continued if we have at least two terms. In this case, we shall have 0 and 1 as our terms. 0 as our first term and 1 as our second term. So what do? We add 0 and 1, the first two terms together, and we shall have 1 that comes after our sequence. Then the next two sequence now would be 1 plus 1. That means 2. And then 1 plus 2, we have 3. If we need to continue, we will just add the two previous terms to create the next term. Now, is it possible to actually create another type of sequence? Yes. So later on, you can perform a Fibonacci sequence despite using different numbers in each term. But we will now focus on the relationship between the Fibonacci sequence and the golden rectangle. So as mentioned before, Fibonacci sequence is related to the golden ratio, which means it can also be represented in the golden rectangle. So suppose we have a rectangle whose dimensions are 1 by 1. That's the first square. Or a square is a rectangle. So the next square for that is another 1 by 1 square. So the dimensions of the next square would be 2 by 2. Given this, we would now know that our next term, or the dimension of our next square is 1 and 2. So that's 3. And then 2 plus 3, that's 5. And 3 plus 5, that's 8. Can we continue this rectangle? Of course. We can continue this with our next square, that is 5 plus 8, 13. So 13 by 13. What relationships can we get out of this rectangle only? So remember, the Fibonacci series is 1, 1, 2, 3, 5, and 8, so on. It can be continued. So the first question is, suppose we get the number relations in a Fibonacci series, like squaring each numbers in the Fibonacci series, what can we get? So first off, square each number. So when we say square, we are going to multiply the numbers in the Fibonacci sequence by itself. So 1 times 1, 1 times 1, 2 times 2, and so on. So we shall have this. So if we are to continue this, sorry, so the answer to squaring each terms in the Fibonacci series are the following. So notice, if we add 1 and 1, and 1 and 4, for 9, 9 and 25, and so on, our answers are the following: 2, 5, 13. And these numbers are still found in the original Fibonacci series. So that's one of the amazing things that we can actually derive when we use the Fibonacci series. So it's just amazing that even if we already square the numbers, once we add the terms from squaring each terms in the original Fibonacci series, we will still get its answers, or we can still find its answers in the original series. Now, notice, if we get the area of the rectangle, so given this series now, we have two ways to actually get the area of the rectangle. So the area of the square is to multiply the sides, meaning to square each terms in the Fibonacci series. So that's 1 times 1, 1 times 1, 2 times 2, and so on. Hence, the entire rectangle is, the area of the entire rectangle is actually 104 if we add all the squared terms of the Fibonacci series. But we may also use the area of the rectangle, which is length times width. So in this case, the length here, this part, so 5 plus 8, that's 13. And then this one is our width, that's 1 plus 2 plus 5, that's 8. So these are the terms, the length and the width and the length, and the area is the same, 104. So this is when we only want to get number relationships. In other words, we can play with the numbers in the Fibonacci series, and interestingly, we can get answers that would still be found in the original series. Aside from that, since we have been talking about the Fibonacci sequence and the golden rectangle, we can then assure that it's also related to the golden ratio. So how do we get the golden ratio here? Notice, if we divide the terms, the first two terms, 1 divided by 1, 2 divided by 1, 3 divided by 2, 5 divided by 3, and so on. Notice how the answers are getting closer to the golden ratio value. Remember that our golden ratio is equivalent to 1.618. So as we start by dividing 55 divided by 34, we now get the approximate value of 1.618. 89 divided by 55, is also approximately equal to 1.618, which means the numbers that will follow after 89, and if we divide it by 89, Succeedingly, we repeat the same process. The values that we will get will now be approximately 1.618. So what can we conclude in here? So the higher the values of the terms in the Fibonacci series, the closer the ratio of those numbers to the golden ratio. So starting from 55 divided by 34, we already get the approximate value of 1.618. And the golden ratio is approximately 1.618. So kung i-continue natin ito, we will still be getting 1.618. So how do we generate our own Fibonacci sequence? It's fine if you are going to use different numbers with the idea of repeating it according to the rules of the Fibonacci sequence. So never mind the formula. To make it simpler, we are going to get the next term by adding the first and second terms together. Best is to have an example. So notice if our first term is 1 and the second term is 2, and you're assumed to create 5-term Fibonacci sequence. So the first two terms were already given. We have 1 and 2. So 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, which means our first 5 terms in the sequence would be 1, 2, 3, 5, 8, and so on. Now, if you're given 0 as your first term and 5 as your second term, the following is your sequence. So we have 0, 5, 5, 10, 15. Then we also have a first term of 3 and 7. So basically, we add the first two terms to get the next term, or the two previous terms to get the next term. That's it. But this will only be practical for the first few terms in the sequence. Suppose around 5 terms to 10 terms. But this will not be very practical if we are to get the 30th term, the 20th term. That would be a very tedious process and it will take us a longer time to finish. So the best way to do that is to use the Bennett's formula. The Bennett's formula is in this 1 divided by square root of 5 multiplied to the quantity of 1 plus square root of 5 all over 2 raised to n minus 1 minus square root of 5 all over 2 raised to n. How do we do that? Suppose you are to find the values of 20th term and 25th and 30th terms. The answers to these are the following. How? I don't recommend you solving this one using manual process. I'd recommend you use a calculator. And to do that, this is how you're going to input it in any types of calculator. We have the old model type and the newer calculators, which means you can also use it when you download scientific calculators online. So what I can say is be generous when using parentheses, it's fine, but make sure that if you had an open parenthesis earlier, make sure to close it. So make sure that they are paired together. So since this one is a quite complicated value, unless our calculator is the newer versions, I think in the old calculator, you have to be careful. So 1 divided by square root of 5, the divide function is that inverted little L something in the calculator. You can see it below the shift function. And this is an arrow pointing to the top, which simply signifies exponent. So for this one, why do you need to put this inside a parenthesis? So I have explained this one before in the mathematics as a language that if it's quite complicated, the calculator will straight is very straightforward. Will read it according to how you input it. So it's better if we put complicated parts in the formula inside the parentheses so that the calculator can properly identify it and not mistake the calculation. Because despite using a calculator, you might still have a mistake in the calculation. So at some point, it's possible that you will have decimal values when computing if the values are or the numbers are not actually input properly in the calculator. So for this one, we have parentheses and then the fraction bar and square root of 5. Make sure that your parentheses are paired properly. So in this case, they are paired together. This one is paired as well, and so on. Because if it's not paired properly, you will have a problem along the way. What I mean by problem is that, again, the calculator might produce a syntax error message, meaning a manual input error or a math error because it's not solvable. But definitely this should be solvable. In the new calculators, you don't have to uh, make an issue when it comes to inputting fractions because you can just input it as how you see it. It's just that the grouping symbols are all parentheses. So you cannot actually use brackets or braces and the likes. So just assume that they are brackets despite them being input as parentheses. So that's how you're going to use. So if this one is if you can properly input this one in the calculator, and then I'm sure that you will get the correct answer. That's it.